All right, so good morning, everyone, and thank you to the organizers for inviting me to speak here. I'm very excited to be giving the first talk of this conference on quantum error correction. Of course, the truth is I personally don't really work on quantum error correction per se. I work mostly on quantum chemistry and quantum algorithms. I work closely with a lot of people like Austin Fowler and Craig Gidney on compiling these applications all the way down to sort of assess the resources required for fault tolerance, and so I hope some of you will find that interesting. So at Google, ultimately, we do intend to build a fault-tolerant quantum computer. And for us, we think sort of the first useful version of this device would probably have something like 100,000 to 1 million superconducting qubits on a planar array, and we'd be targeting something like 10 to the minus 3 error rates and the ability to distill magic states in about 200 microseconds. So what sort of interesting and classically intractable problems, if any, can we solve with a device like this? Well, if you know me, you know that my answer is something along these lines, that systems of interacting electrons are sort of a near ideal application for devices like this because classically they're very challenging to simulate, but they're also potentially quite interesting. So to take some examples from chemistry, exactly solving this methane molecule, I can do that in seconds on my laptop, ethane maybe minutes, propane's already getting quite hard, a cluster would be helpful for something like that. Now obviously we'd like to look at more complicated chemistry than systems like that. So specifically, what kinds of problems do we want to solve? Well, one problem that's received a lot of attention is this problem of nitrogen fixation. So this is how humans make fertilizer, basically. And 70% of the nitrogen atoms in your body have been through a reactor doing this. It consumes about 2% of the world's energy, and fertilizer plants explode sometimes, and it's not a very green process. However, there are these bacteria that live in the soil. They have this enzyme called nitrogenase. Nitrogenase has this sort of magic catalyst at the center of it, which is called FOMOCO. And FOMOCO does this reaction at room temperature and atmospheric pressure. So it'd be great if we could develop sort of an industrially scalable form of this. The problem is we have almost no idea how the electronic structure of this system works. So it'd be great to try to simulate it with a quantum computer. So the first paper in our field that looked at that was from Microsoft, and they looked at this, it's called 108 qubit active space that just sort of studies the crucial part of the chemistry there. So unfortunately that work concluded, they sort of tried to optimize things as far as they could. They found that something like 10 to the 14 T-gates at least would be required. And on the topological platform that Microsoft had in mind, that turned out to be somewhat reasonable numbers. But for the architecture that I've described, state distillation alone would take something like a gigaqubit month. So 1 billion qubits distilling magic states for a month, or 30 billion for a day. And that seems pretty far away to me. One of the results I'll talk about today looks at actually an even larger and more accurate representation of this system. And we have a new paper out showing that we can do it in fewer than 10 to the 11 T-gates, which is an improvement, but we're still talking about state distillation taking a megaqubit week, which is looking a little more realistic, but high overheads. However, I'll also talk about some different sorts of problems in chemistry, ones pertaining to simulating solid-state materials, which look a good bit more practical. We had a paper last year that showed there were some kind of interesting classically intractable instances you could do with about 10 to the 8 T-gates, requiring about 800,000 physical qubits in 3 hours. And we had an even more recent paper showing that under some circumstances that are a bit more limited, and I'll talk about that, you could get away with doing interesting instances with about 300,000 physical qubits in about an hour. And in the context of solid-state materials, we're thinking about periodic systems like graphene, or the things in solar cells, usually the cathodes in batteries to make electric vehicles, and superconducting models like the Hubbard model. But I'll say more specifically what we have in mind there. So sorry for those of you who have seen this kind of slide from me a lot, but since this is a quantum error correction conference, I should give some background on chemistry. We're trying to solve for the energy of a molecule. Here's the simplest molecule. It's got 2 protons, 2 electrons. These things interact through the Coulomb potential, and they have kinetic energy. But typically in chemistry, we sort of clamp the nuclei down, and we just solve for the wave function of the electrons, and that's a very good approximation within chemistry. Once we do that, it's called the electronic structure problem. And once we've sort of clamped these nuclei down, the concepts of energy surfaces exist. So we can plot the energy of this molecule as a function of where the nuclei are, for instance. And these surfaces tell chemists a lot of information. in fact, the sort of difference in energy between extrema inform our understanding of chemical rates. So in this case, for instance, the rate at which the molecules, flying apart or coming together, because that's all it can do. But in more complicated reactions, knowing these rates allows us to write down differential equations, which can predict essentially everything that's going to happen in the chemistry. However, these rates are exponentially sensitive to these changes in energy, so we need to know them very accurately. And it's obtaining that accuracy which is so challenging classically in many contexts. There are a lot of classical methods that can do sort of good approximations to structure, and they can get the energy somewhat correct, but typically not correct enough to get chemical rates, especially not for so-called strongly correlated systems, which are some of the examples that we'll focus on. I should mention furthermore that there's often these large molecular systems we're interested in, but usually it's necessary only to put some of the electrons in like an explicit representation on the quantum computer. And a lot of the environment can be treated using lower levels of theory. There's a lot of infrastructure that's fairly well developed for this. Okay, so what are we actually going to use the quantum computer for? So usually the approach is to use some classical approximation to prepare, say, a ground state or an excited state we're interested in very approximately. And that's typically something we can do quite well in chemistry. And then what we want to do is we want to sample in the eigenbasis of the Hamiltonian using a quantum algorithm in order to project ourselves to, say, the ground state that we're interested in. And there's a number of different ways to do this. Perhaps the simplest and the one that the original work on quantum chemistry from Gusick and many papers that followed looked at was performing phase estimation on the time evolution operator, which is sort of simple enough. But recently, a lot of the most performant techniques have looked at performing phase estimation on a different unitary, which is actually a quantum walk, which is sort of best thought of as time evolution under the arc cosine of the Hamiltonian. But it shares an eigenbasis with the Hamiltonian, and so that's sufficient for our purposes. The way that these quantum walk algorithms work, I'm going to talk for a little bit now about the algorithms. We'll get to some error correction stuff, don't worry. But the way these quantum walk algorithms work is based on what's called LCU methods, linear combinations of unitary methods for Hamiltonian simulation, which begin with expressing the Hamiltonian as a linear combination of unitaries. I'm going to use this notation here sort of throughout my talk. So in particular, one of the most effective strategies for this was introduced by Guanghao Lo and Isaac Chuang, and it's called Qubit Ization. And what Qubit Ization is it's an oracular framework for creating these quantum walks. Specifically, it says suppose, and it doesn't say how you do this, but it says suppose you had a circuit that did the following. We call it select. And what it does is it acts on a register L that indexes the different terms in the Hamiltonians, and it selectively applies one of these unitaries from the linear combination of unitaries to the state. And then suppose that you had one other circuit, which we call prepare. And this one, it creates a superposition over this index register with amplitudes that are weighted by the coefficients of the terms in the Hamiltonian. And there's a normalization parameter here, lambda, just the sum of the absolute value of the coefficients, turns out to have pretty significant ramifications for the complexity of the algorithm. So how you implement these things, I'll describe a bit, and it's not part of Qubit Ization. Qubit Ization just says, suppose you had these. Then you could create the quantum walk we're after, create the evolution under this arc cosine, which is what's needed to do the phase estimation we're trying to do, just with this simple circuit here, one application of select and two applications of prepare. And furthermore, in this PRX paper of ours from last year, we looked at using this in sort of an optimal fashion within phase estimation and showed that very specifically, if you could repeat this quantum walk a number of times at square root 2 times pi times lambda over epsilon, then you could estimate the energies of the system you're interested in to within air epsilon, which is our goal. So that's exciting, but we're not finished yet. You can't just apply Qubit Ization to chemistry and call it a day. You have to actually figure out how to realize these things. So I'll say a couple of things about that in kind of broad terms, and then I'll connect it to some like actual problems that we've solved in chemistry. So first we'll focus on this select oracle. Again, we're selectively applying one of the terms in the linear combination of unitaries. So one thing you could do, of course, is you could just have a totally controlled solution where if there's L terms in this linear combination of unitaries, you could just totally control L operations. You'd have some gate complexity L log n if the operations are up to n local, but that is not a very efficient strategy. So it's better instead to think about exploiting some structure in the Hamiltonian. I'll say a little bit more about where this chemistry Hamiltonian comes from in a few slides here. But generally, we're dealing with fermions that interact pairwise, so we can always write its Hamiltonian in second quantization in a fashion that looks like this, where these HPQRS are just scalars that are usually coming from integrals. And if we are going to map these things to qubits, we have to remember fermions are identical antisymmetric particles, so they have a certain algebra, so you use something like the Jordan-Wigner transformation. Now, I'll point out that this is not a linear combination of unitaries as written. These things aren't unitary. However, it will be helpful for our purposes to just add some notation where we're going to write these Rayleigh and Lorentz operators in terms of Majoranas. So this Majorana operator is the XZZZZ thing, and then you see on the right part here, if you multiply Z times that, you get that IY part. And if you do that, you can write out the Hamiltonian in a form that looks something like this, where there's actually sort of 16 terms here because the Z's can be in all sorts of different positions. But now the Hamiltonian is a linear combination of unitaries. And furthermore, each of the terms is a product of a number of things that are unitary, either Z or these Majorana operators. And that allows us to use a strategy that looks something like this. Instead of just having one register that indexes all of the terms, and there's n to the 4 terms, so we'd have 4 log n registers anyways, we just have 4 registers, one for each of the indices we're summing over. And first, we can apply one of the Majoranas controlled on the P register, and we apply one controlled on the Q register, and so forth. And it's apparent we would just need sort of 4 repetitions of circuits that do something like this in order to achieve our goal, which potentially has a lot less complexity than just totally controlling on all of the terms. I won't get into the details of this, but in some of our recent work, we're able to do this furthermore with T complexity that's exactly 4n, as opposed to something like n log n like you might expect. So it turns out this part of the problem is usually the easy part for chemistry. The much harder part typically is this so-called prepare oracle, preparing this state. And that's because there's a lot of structure in these coefficients in the chemistry Hamiltonian. So one thing you could try doing, this might only make sense if you have some idea of where the chemistry Hamiltonian comes from, but you might try actually computing these coefficients on the fly, like doing the integrals on the fly. And that was actually something we looked at in a paper from 2016. It makes some sense asymptotically, but it's a very impractical strategy. Rather, the sort of vast majority of papers in the last couple years have focused on a different approach, where we basically use a circuit that sort of loads the coefficients that we're interested in into superposition from a database. And so specifically, I'm talking about a circuit that we've taken to calling QROM, which does something like this. It's kind of like QRAM, only it's a real thing. We give explicit circuits for it in terms of T-gates and so forth. But also you can't write to, or read from it, or write to it the way you can with QRAM, so it's quantum read-only memory, I guess. But this is what it does. It's just loading these elements D sub L from a database into a superposition over L. So in this PRX paper of ours, we show how to do that with exactly T complexity 4 times L, where L is the size of the database. And it's kind of interesting, it doesn't depend on the size of the entries, just on how many of them there are. There was another paper, this one is from people at Microsoft, and we had sort of a different approach in a recent paper, which sort of actually improves this in a surprising way, such that you can actually have complexity of L over G if you have G dirty ancilla available. And during this step, we're usually not doing anything to the system register with n qubits, so this is usually a good idea. So it turns out that usually this entire state preparation can end up with scaling that's just determined by the QROM step. I'll say specifically how we tend to do that. Some of you might kind of glaze over on this slide, but soon we're getting to error correction stuff, I promise. So we start with a superposition over this index register, and then we use QROM to load into superposition some values that I'll call alt-L and keep-L, which are some classically pre-computed values that are related to the W sub L. And then what we do is this strategy we called coherent alias sampling, and the idea is that we're going to swap the L register and the alt-L register with a probability that is given by the keep L register. And if we've chosen those values correctly, we're going to create this state, which is the state we want up to being entangled with some junk. And for various reasons, for our purposes, that being entangled with junk just doesn't matter. And so there's some classical algorithm that figures out alt-L and keep L. Basically, Here you can think about the x-axis being the different L values and the y-axis being the different square root W's that we wish to have as amplitudes. And what we're going to do is we run a classical algorithm that kind of repacks things so that each value of L is associated with its original value and an alternative value. And sort of the ratio of these things determines that keep L value. And it's an efficient classical algorithm we actually provide code for. So the main point of this is, and this will be important for understanding some other things I'm going to talk about. For most of these algorithms for chemistry, the bottleneck step is basically just the QROM, which the cost of that is basically how many pieces of unique information do you need to load into superposition. Okay, so given that, we need to now talk a little bit about the different chemistry Hamiltonians we might deal with. So typically in chemistry, we write systems in a molecular orbital basis, which is a very compact basis, meaning that you don't need very many qubits to describe a molecule very accurately. However, the drawback to an approach like this is you end up with a very complicated Hamiltonian that has n to the fourth terms at all system sizes, which means the QROM is going to be rather expensive. So we had a different paper from a couple years ago that said, if you're willing to give up some of that compactness, and you choose the basis in sort of a careful way, then there are some bases for which this Hamiltonian has only n squared terms, and you could write it in a form that looks something like this. So it turns out that basis we used was derived from a unitary rotation of plane waves. Now, plane waves are a periodic basis, which makes them very well suited for periodic systems like crystals, which are periodic in 3D, or graphene, which is periodic in 2D. If you wish to treat single molecules with plane waves, though, there's sort of a problem because they're not periodic and their density dies off in space, whereas plane waves don't. So it turns out you need a large constant factor more plane waves than molecular orbitals to treat single molecules. And as a result of this, you need a lot more qubits. So it's not particularly good for that. But nonetheless, simulating things like crystals and graphene is interesting. So this more recent PRX paper of ours focused on compiling the LCU methods I just described for simulating Hamiltonians like this. And I won't bore you with some of the details, but we're able to do the prepare oracle at a cost that's only 6n. That's the T complexity, plus some log factors. Now you might say, well, there's n squared terms in this Hamiltonian. How did that happen? It turns out there's translational invariance, which I highlighted by writing the coefficients as like p minus q instead of p comma q. And so there's only n unique pieces of information you need to load. So the QROM only has cost order n, and that's how we get that. The select part, because the prepare was so incredibly efficient here, the select part's actually even slightly more expensive. It has cost 12n. And again, there's this lambda parameter, which is the sum of the coefficients of the Hamiltonian. But putting this together, we get a T complexity for the whole algorithm for exactly solving the chemistry problem, which is given by this closed form 24 square root 2 pi n lambda over epsilon, which is kind of exciting because it's the first time in like decades of people working on quantum algorithms for chemistry that we've actually sort of gotten a closed form for the cost like that. So that was kind of interesting. And now we can, there are a lot of circuits involved. Now we can finally talk a little bit about, error correction. So I probably don't need this review-ish slide for a lot of you, but this is an AND gate, and you can do that very fast on a classical computer. On a quantum computer, it's a little challenging. You have to, do these, sort of stabilizer measurements or something to realize it within an error-correcting code. And, each of these T gates requires some T state, which comes from magic state distillation, and you have some horrible looking thing like this, a T factory here that's required to produce those states, and is quite slow. So, maybe 1,000,000 times slower to apply an AND gate on a quantum computer than a classical computer. So we've got to be kind of careful about that. Now this was, there's a long history of people developing a magic state distillation. This was one of Austin Fowler's braided T factories, which in our context had about 150,000 physical qubits. But there have been a number of recent improvements, and again, there's a long history of developments here. These are not, the original inventions of magic state distillation, but this is the one we were looking at in our PRX paper. There was this work by Daniel Latinsky that used lattice surgery to shrink the space-time volume pretty significantly. And there was some more work by Craig and Austin, which used directly distilled Toffoli states, which were actually the bottleneck in our algorithm, and did some other things to shrink the volume even a little bit more. So ultimately, these improvements over the previous braided factories require maybe about 3 times fewer qubits and are about 3 times faster, roughly, in our context. Still, it's looking like it would take about a week to distill about 1 billion Toffoli states if we were distilling in serial, meaning we just had one factory doing magic state distillation or Toffoli state distillation, which means if we're trying to keep the footprint as small as possible, we should try to have less than 1 billion Toffoli gates or something like that. I should note too that Daniel Litinsky had another paper this year, which we haven't really actually laid things out all the way, and so we're still not quite sure exactly how this would change numbers, but there's some ideas about if you distinguish between qubits that are used for error detection and the ones that aren't in magic state distillation, you can reduce the code distance for some of them and save a lot of qubits that way. So we're optimistic there's a lot of improvements to be made here as well. So for the algorithm I was just describing, we ultimately compiled all of the bottlenecks to the surface code, both by hand. And Craig made this one. This is one of our bottlenecks. Also, Alexandra Taylor, who we worked with, had an automated system that we used as well and gave ultimately kind of similar numbers, which gave us some confidence we were doing things correctly. In both cases, we were able to confirm that for these algorithms, a bottleneck actually was state distillation, which is good to know because if you optimize things just for T-gates too much, you could run into problems occasionally. And we looked at estimating the resources for some specific systems we thought would be interesting, some different like unit cells of crystalline solids like diamond and graphite, LIH metal. And something that's really nice about these LCU methods is it turns out that the only way that like the specific instances change the cost beyond just the size is through this lambda parameter, which is somewhat insensitive to the particular instance. Which differs a lot from, say, Trotter methods, as I'll mention in a moment. And so we also looked at using these algorithms for simulating the Hubbard model, which is a lattice model often used to understand superconductivity that a lot of people study. And so here are some numbers. Basically, we're looking at different instances of the Hubbard model and electronic structure here. And we're giving how many physical qubits would be required at 10 to the minus 3 error rates, 10 to the minus 4 error rates, and how long things would take. And as we can see, we can error correct instances that would be quite challenging classically with well under 1 million physical qubits and in just a couple hours of runtime. So this is sort of the first time we've seen that in chemistry, and for us, that was very exciting. So good progress there, I think. You might be wondering, well, all that LCU stuff was really complicated. What about product formulas? Just good old-fashioned Trotter where you do something like this. Use your Hamiltonians as sum of terms, and you just sort of simulate them one after another. Well, the thing about Trotter methods is that they tend to scale polynomially in, of course, the number of qubits, but also polynomially in the number of terms in the Hamiltonian, which I'm calling L here. And that's because you just typically have to simulate each term at least once. Earl has some methods which are avoid that, but generally you see that. And also Trotter methods, unless you go to arbitrarily high orders, which appear impractical, they also have polynomial scaling in the inverse of the precision that you desire, which tends to be a very stringent precision requirement in chemistry. By contrast, the LCU methods, they scale, of course, polynomially in the number of qubits, but potentially they scale polylogarithmically or logarithmically in the number of terms or in the inverse precision. So you'd think that they would have an advantage. But especially thinking about this precision part, for molecules, we usually want fixed precision, the precision needed to predict chemical rates. But often when we're looking at condensed phase systems like materials, we're actually okay with an error that grows with system size. If you think of just simulating a material that is a periodic thing that's sort of infinite in size, and what we're doing is we're just explicitly simulating bigger and bigger chunks of it with periodic boundary conditions. Well, the infinite material has infinite energy, so you can't really be truly interested in the energy of this bulk material. You're of course interested in something like the energy per unit cell. And it turns out that then if you allow your target energy to grow with n, you have to be kind of careful with the analysis of the Trotter errors because a lot of the techniques based on perturbation theory don't work. But in a lot of cases, the Trotter methods will actually sometimes scale better than the LCU methods when you're allowing yourself this error that scales with n. I'll say, though, that unlike LCU methods, Trotter methods are really, really a pain to analyze. They're simple to understand, very hard to analyze. You need to do sort of numerical simulations, which can be pretty costly, and the scaling tends to be very instance specific. Nonetheless, we looked at that in this recent archive paper. We did it for the Hubbard model and for quantum chemistry. And I want to point out that the Hubbard model results were particularly striking. So here I'm applying the T count required to solve some instances of the Hubbard model such that we predict the energy to within 0.5% of the ground state energy, which is a difficult target to achieve classically, as a function of n. The different lines are some different types of implementations, different ways of doing the Trotter steps that we looked at. And for some of the implementations, you see this bizarre fact, which the T complexity actually is sort of independent with respect to n. Now, what's happening there is the Trotter step for the Hubbard model costs O of n gates, but when you allow yourself an error that's growing with n, the number of Trotter steps required is actually decreasing linearly as a function of n. And eventually you're going to hit one Trotter step, and you can't do less than one Trotter step. So in a true asymptotic sense, we don't have constant scaling, but that point is predicted to happen at tens of thousands of orbitals. And so up until that point with this algorithm, we actually can do Hubbard model simulations that cost us sort of O of 1 in terms of the T complexity, which is quite interesting. The story wasn't quite as good for electronic structure. And specifically, these electronic structure numbers were specific to the uniform electron gas because, like I say, Trotter is very instance specific in the way that it works. But these numbers, I think, are quite encouraging too. So again, these are all targeting a target error of 0.5% in the total energy, which is different than the absolute precision target in the previous slides. But you see in these certain contexts, we have significantly better scaling. The physical qubits required to solve some classically hard instances of the Hubbard model, for instance, even up to 512 qubits is actually less than, it's certainly less than 1 million. And at 10 to the minus 4 error rates, we have some that are less than 100,000 physical qubits. So I think that's pretty exciting. And the runtime here is in hours or less than hours. You might notice there's something weird going on here where it's like the bigger model is faster to simulate. That's because there's certain sort of magic numbers here, and if you have something that's like 2 times, it doesn't matter. Like 512 has some reasons why it's easier to simulate than 200. So anyways, there's definitely some progress there, and we're happy about that. Okay, so far I've talked about simulating lattice models and simulating these plane wave Hamiltonians, but what about simulating things like FOMOCO, like real molecules in chemistry? So the challenge there, again, is that this Coulomb operator has n to the 4th terms. But it turns out there's some additional structure that we can exploit here. And so you'll have to bear with me a second here, but I'm going to explain how we exploit that structure. So these coefficients of this operator we can think of as a rank 4 tensor. And what I'm going to do is I'm just going to sort of reshape, using numpy.reshape, for instance, this tensor from an n by m by m by n thing into a matrix that's n squared by n squared, which I'll call W. And then I'm going to diagonalize it. And this is just some notation. The eigenvectors of that n squared by n squared matrix are G, and the eigenvalues are going to be lambda. Turns out it's well known in chemistry that due to the structure of the Coulomb kernel in real space, which is pairwise in nature, this W matrix, even in an arbitrary basis, even at small sizes, is low rank, meaning that most of its eigenvalues are 0. It has only order n non-zero eigenvalues. So what this allows us to do is it allows us to rewrite the Hamiltonian. This diagonalization allows us to rewrite the Hamiltonian in this form. We're writing this, this term with 4 indices as a sum of order n different squared arbitrary-looking one-body operators. And there's some kind of confusing notation here where I'm again reshaping this G so that now it's like a matrix, and that's the PQ element of it. It turns out that that one-body operator we're squaring is also something that we can diagonalize, and here's some more notation for that. And it turns out that, at least in the thermodynamic limit of looking at very large systems, that one-body operator is also low rank. However, unlike the low rankness of W that we can realize at very small sizes, the low rankness of this one-body operator only occurs for truly very large systems, so probably won't help us for our resource estimates that I'm about to discuss. Nonetheless, I know this is pretty terrible, but ultimately the point is that I can write the quantum chemistry Hamiltonian like this. And once I map that to qubits, I have a form that looks like this. It has only n to the 3 pieces of information in it. and this is a linear combination of unitaries. So furthermore, I'll point out that these matrices that diagonalize the one-body operator, these unitaries, they're just a change of single particle basis, and we have some techniques from another paper that shows how to implement them very efficiently. So again, sorry to sort of subject you all to that, but the point is that in terms of the fault-tolerant resource estimates, we had a paper with Dominic Berry from February, which shows how to implement this prepare oracle in a way that takes advantage of that low rank factorization, and we can do the prepare oracle much more efficient. And we also use this dirty ancilla QROM so that instead of needing to load into superposition n to the 4 values, we only need to do n to the 3, and this dirty QROM allows us to sort of fan out in a way that the t-cost is only n to the 3/2. Ultimately from this, we achieve a t-complexity of n to the 3/2 times lambda, which is about n to the 4, and we're talking about arbitrary basis chemistry. And we applied that to the systems that people looked at previously for FOMOCO, including this 108 qubit active space that the Microsoft people focused on. However, there was this paper, which was from Garnet Chan's group at Caltech last year, which said there were some problems with this previous benchmark, and they proposed an alternative active space that had more qubits and didn't have those problems. So we ultimately focused on this larger active space, which you would have thought would have been harder for us to simulate. In this plot here, I'm sort of showing there's a strategy where we have to determine exactly where to truncate the eigenvalues from this matrix factorization that I was just describing. And you might wonder, you know, how quickly does this behavior set in, and how much can you really win from truncating? I mean, in general, there would be n squared eigenvalues, so 152 squared eigenvalues, but what this plot is showing is that it's completely sufficient to choose just 200, which is a number a lot less than 152 squared, so there's some savings there. And ultimately, by doing this, we're able to, for this 152 qubit active space for FOMOCO, reduce the cost to 8 times 10 to the 10 Toffoli gates, which is more than 1,000 times speed up. And things are starting to look, I think a good bit more realistic now. We'd still need roughly a mega qubit week of state distillation. So, you know, 1 million qubits distilling for a week. We haven't done the entire footprint, the whole surface code layout for this algorithm yet because, well, it's a lot of work, and frankly, I think there are some things we can do to make it even better first. So we're going to work on that and then lay it all out. But I think, you know, that's some good progress there. So one of my last slides here, I want to kind of go over a couple error correction relevant ideas that I didn't have time to discuss. Probably that's fortunate for many of you. Anyways, so a lot of the techniques we've been discussing, we also had a paper where we applied them to simulating what is called the Sachdev-Yeh-Kitaev model, which is a fermion Hamiltonian that looks like the quantum chemistry Hamiltonian, but with totally random coefficients. So it's the end of the 4th terms and totally random coefficients. In this model, condensed matter physicists say that it's, you know, some sort of model of a black hole, which is obtained through, you know, ADS-CFT duality, essentially. You'd think this thing would be very hard to simulate because it has end of the 4th terms with totally random coefficients. But the fact that coefficients are random is, in a sense, a sort of structure. Because what we end up doing is, instead of using QROM for the prepare oracle, we actually just apply a random quantum circuit, which creates the, you know, random amplitudes. And if you're sort of careful about how you do that, it creates random amplitudes with the right distributions. And so it actually turns out to be easier to simulate the chemistry. And you could do some things with about 10 to the 8 T gates that would be classically intractable. Another thing that we've been working on, which is not compiled all the way to T gates yet, so I figured wouldn't be appropriate to talk about here, is another way of dealing with this basis error problem associated with the plane waves is you still use the plane wave to simulate even molecules, but you work in first quantization. So in first quantization, instead of sort of keeping track of if there are electrons in a bunch of different places in space, you keep track of, you know, where is each electron in space. And so ultimately you need only a number of qubits that's eta log n, where eta is the number of electrons and n is the number of basis functions. And we're able to show an algorithm with 8 to the 8/3 and to the 1/3 T gates. So this means you could potentially use a very, very, very large number of plane waves and still have a practical simulation. You could use 1 million plane waves, for instance. And with 1 million plane waves, you're going to have some very accurate simulations, even of single molecules. But this technique is described asymptotically. It needs a lot of work to come up with the constant factors, and we're doing that, but it's kind of tedious. Another thing that really isn't about fault tolerance per se, but this is actually work that I was part of, but Zhang Jiang from the Google group was sort of the one leading it, was about mapping fermion models that are lattice models in d dimensions to qubit models that are lattice models in d dimensions. And there have been other techniques for that in the literature as well, by Verstraeten, Sirach, and also Whitfield and Setia and some other people, and Bravi and Kataev. But ultimately, we were able to do this in a way that we could show the mapping itself is also a 213 error correcting code, and also has some other properties that make the encoded system even easier to simulate than the original system. You actually have lower gate complexity for simulating the encoded system than for simulating the original system, and it also has these properties. Now, in terms of, say, a NISQ algorithm, it still looks a little bit hard to exploit the NISQ or the error detecting properties because there's like weight 12 stabilizers. But there was this other work which we did together, which was led by Jared McLean from the Google group, which was sort of a technique intended for the NISQ era, which shows how one can use some extra circuit repetitions, extra measurements essentially, in order to obtain the expectation values of a computation after it is sort of projected into some code or some sort of known symmetry manifolds. And it does this in a way that doesn't require extra controlled operations like syndrome measurements or anything like that. So for instance, this could be a pretty practical way of exploiting the error detecting code properties of these fermion mappings. So that's something that we're kind of excited about. I should mention that both Jared and Zhang are interested in hiring postdocs at Google who would work with them on these sort of NISQ ideas where error correction might come in handy. So you should talk to them about that. But in general, I sort of just want to end with asking the question of, with this architecture we have in mind, with 10 to the minus 3 error rates, can we ultimately error correct interesting instances with less than 100,000 physical qubits? We're not quite there yet, but I think that through both continuing to push on the algorithms, the representations in chemistry, and better techniques for things like state distillation, we can certainly get there. And I also believe that we can error correct molecules like FOMOCA with less than 1 million physical qubits. And hopefully we'll be there pretty soon, in fact. So I want to thank a few people. There were a lot of authors involved. I talked about a few papers here, and there were a lot of people involved. But in particular, I could not have done this stuff without Dominic Barry, Craig Gibney, and Jared McLean. I want to emphasize Jared is actually at this conference and will be looking for a postdoc to work with him on quantum error correction related ideas. So anyone interested should definitely find him and talk to him about that. Also, Nathan Weeb, Austin Fowler, Ian Qubit, and Mario Moda were extremely helpful, and others. So with that, I'm going to end with one of my sort of signature tables here, in case people are not sufficiently confused enough about how some of these recent papers relate to one another. And I suppose I'll take some questions.
Questions for Ryan? Ken?
Yeah, so Ryan, towards the end you had this kind of funny 213 code, and I know that 2 means 2 dimensions. Can you remind me how many physical qubits it is? Do you remember?
Yeah, it's the number of physical qubits you need is twice the number of fermion modes. So yeah, if you want to encode what would be n qubits, you need 2n physical qubits.
Okay, so in your plane wave-based algorithm, you need scaling with the number of fermions. Do you need to...
The first quantized one, you mean? Yeah.
Do you need to know, in order to do this, do you need to know the number of fermions, or can you have superficial?
Yes, in first quantization, so that is sort of essential to first quantization, is that you do, well, at least any construction of it that I've thought about, you would need to be in a fixed particle number manifold, and that's actually one of the symmetries you're exploiting.
Thanks.
So yeah, doing, usually in chemistry that's the case unless you're doing like a Dirac equation thing, and that's not very typical.
Anyone else? Okay, yeah. I think I might ask one question actually. So there was this part where you were talking about plane wave problems or problems with periodic lattices versus molecules. Mm-hmm. And you said that in some cases, Trotter methods might be competitive against LCU for the periodic systems, but I kind of lost thread of what the argument was.
The circumstances in which the Trotter methods appear to sometimes have an advantage, which in some cases is substantial, could be more than an order of magnitude, is a circumstance where you're not looking for a fixed additive error. You're looking for an error in the energies, for instance, which is allowed to grow with system size. So when you'd be targeting something like the error per unit cell as opposed to like a total error or absolute error.
So the LCU method has a worse scaling with epsilon.
Yeah, well, I mean, it depends on the perspective. So the LCU methods, they scale logarithmically with respect to 1 over epsilon. And the Trotter methods, they scale like polynomially in 1 over epsilon. So if epsilon is small, you'd say the Trotter ones are scaling worse. But if the epsilon is growing, then this difference diminishes.
Okay. Any more questions? If not, we'll thank Ryan. Okay.